All right, cool. So welcome to week 4, which is kind of crazy because next week's the halfway point. So we are flying through this quarter.
It's weird to think about.
I know, yeah, it's just going like ridiculously fast. But we're in good shape here. But we're going to keep getting into new things. So let's start with homework questions. So I already saw a bunch of people in office hours this morning and lab hours earlier. Sorry, go ahead. Was that a question?
I have a question.
Okay.
So I have a quick question on the difference between a PLA map and a PROM map at the bottom with 10 and 11.
Mm-hmm.
So for the PROM map, on the input side where there's the gates and the not gates, we want to list all of the input possibilities in order. So it's like 0, 0, 0, 0, 4 zeros, and then 0, 0, 0, 1, and then 0, 0, 1, 0,
Mm-hmm.
all in binary order, right?
Yeah, and those are hardwired, right? You don't get to set those with fuses in a PROM.
Okay.
But there's a note at the end of 11 which says only list the terms that you're actually going to use, because you actually have 8 inputs for that circuit. So you have 256 min terms, and that's a lot of drawing to do.
Okay.
So for the PROM one, your left side's going to look something like this, right? Except that you have 8 inputs, but it says do not draw unused AND terms. So just list the ones that you're actually going to use to combine with OR gates over here.
You don't do that for number 10, right?
Number 10, we're doing a PLA. So you're going to have a programmable plane over here and a programmable plane over here. But you know, with a PROM, since the AND plane is fixed, the PROM typically contains all possible combinations of inputs and their inverts. So there'd be 256 terms. With a PLA, you get to set those up yourself. Same with a PAL. So
Okay.
yeah, so you don't have to worry about that. All right, so someone wants to go over 3U. So let's take a look at that. This is looking at the idea of
This is due Wednesday, correct?
Sorry, say again.
This is due Wednesday.
I believe so. Check Canvas. So this is looking at the idea of universality of NOR gates and NAND gates. The NAND gate was in part 3S. So here we're working with NOR gates, and there's a number of ways you can go about this. One way to do this is to make a truth table of this circuit and then try to implement that truth table using NOR gates. And if you want to make a truth table, my suggestion is take that circuit and break it down. Think of, for example, the output of this gate. Let me move this out. Think of the output of this gate. Oh, that's a different one. Pick a variable for the output of this, pick a variable for the output of this, make a truth table showing the values of those for all 16 inputs. And then take those two, NAND them, get the value of your circuit's output for all 16 cases, simplify that truth table, and then see if you can write that as a collection of NOR gates. The other way is to get comfortable with this idea of rewriting things in terms of NORs. So let me put down the truth table here. And an OR is just like an OR, but it's opposite. So it looks like that. So if I needed a NOR gate, no problem, I've got a bunch of NOR gates available. If I need an OR gate, how can I get an OR out of a NOR?
Couldn't you invert it?
You could invert, so how do I invert with a NOR?
You take the input and you feed it to one input on another NOR gate? Just one though?
Something like that. Let's think of a NOR gate. So it has two inputs and one output, but we can observe from the truth table if the two inputs are the same, if they're both 0, the output is the opposite. And if they're both 1, the output is again the opposite. So a NOR gate kind of has an inverter inside it, and you can get that by saying if I put X into both inputs, I get the inverse of X coming out. So I can take this and implement it with a NOR gate by just wiring X to both inputs. Okay, so we already have a NOR, and we have a NOT. And if I put those together, that'll give me an OR. So in the beginning of this, we want A or B. Well, we can mimic what we're doing here. We could take A and B and feed those into a NOR gate. That's A or B bar. If we want A or B, we just have to take this and we have to invert it. And we can use our NOR gate inverter. And that's going to be A or B inverse inverse, which is just A or B. So this circuit captures this piece of the circuit we're trying to build. And so you can keep building this up. So these circles, or bubbles as they're called, are inverters. So this is basically C, this is D bar, and those are NANDed together. So the output here is C ANDed with D bar with a bar on top. Well, we have De Morgan's theorem, which says XY bar is X bar or Y bar. So C D bar is going to be C bar or D bar, which is C bar or D. So we can change this thing into an OR gate, where we just want to take the OR of C bar and D. Well, we know how to make an OR gate. If I put C bar and D up here, this will be C bar or D, which is the right side of this piece of the circuit. So we can rebuild this. Where do we get C bar from? We'll take C and run it through a circuit like this. That'll give us C bar. So feed that in here, feed D in down here, and the output over here will be C bar or D, which is this point right here. And then we need to take those two things that we've generated and calculate their NAND. And this is De Morgan's theorem again. So if we have X NANDed with Y, that's X bar or Y bar. Well, we know how to make an OR gate. We've done it 2 times. We can do it once more. So we can take this output, invert it, take this output, invert it, feed those in over here, and your output over here will be your output from here. So this is not a practical exercise, right? It's an exercise in playing around with things like this and De Morgan's theorem and using NORs to do inverses and just kind of seeing where it gets you, right? And it's a very error-prone process. It's not something we typically would want to do, by hand, but it's an exercise, right? Just to sort of explore this idea of different kinds of logic being used in different arrangements to get the same behavior as other kinds of logic. So hopefully that helps.
Could I fine-tune the question on 7, please?
Sure.
When I look at 7s and look at the solution, some things aren't being put together in my head quite right. Like the F1, for example.
Okay.
The 3 and the 6 should be 1s, correct? But it's showing it as noughts. So it makes me question whether or not I got 7u correct.
Well, let's look at F1 here. So this is a demuxer. These bubbles mean that the outputs are inverted. So these are the complements of the minterms, right?
Mm-hmm.
And so F1 is take the complements of the inputs, OR them together, and then complement the output. So this is a bunch of trickery going on. But let's just look at this logic gate. Just this OR with all the bubbles on it. So if we have A and B, and those get inverted and fed into an OR gate, and then we invert the output. That's the inverse of A bar ORed with B bar. And De Morgan's theorem tells us not something or something is the not of the first thing ANDed with the not of the second thing, which is just AB. So this looks like a fancy AND gate, right? So it's the AND or the product of M3 bar with M6 bar. So it looks like that to me. Say again?
Aren't those OR gates?
Those are OR gates, but we just did this, which said this is actually acting like an AND gate. Because we're inverting the inputs and we're inverting the output.
So I have a quick question. Could you end up with a minterm, minterms for one of those functions where it's like 0 and maybe 1, and one of those minterms has a bar over them? Or is that something you can't do, like a bar over a minterm?
If you want something in a sum of products form, it's got to be just min terms, and if you want a product of sums, it's got to be just max terms. You can't have inverses in there. But let's look at this a different way. So there's two ways to look at this. Let's stick with a sum of products. Okay, since it says compact minterm. So this is M3 bar coming out here. That gets inverted again. So the input here is actually minterm 3. And this is minterm 6 inverted, right? M6 bar. But it gets inverted on the input, so this is M6. So F1 is really M3 or M6.
They're not when they leave the mux.
Yeah, they're knots over here when they leave. Yeah.
Okay.
So F1 is the inverse of M3 or M6, which means we can write F1 M-verse as M3 or M6, which is just sum 3 comma 6. So I think that's the form that's in there. F1 bar sum 3 6, yeah.
Okay, I see why it's that way, because I was like, I'm only seeing 2 knots, so why is
Oh, okay.
Now that I see the third one, it makes more sense.
Okay, perfect.
Which makes me think I actually got the S. Yeah, that makes me think I got 7U, right?
Yeah, because 7U, the mux is using positive outputs. Cool.
Cool.
We're going to look at some other circuits that do this kind of thing, and this pops up all over the place. There's always like bubbles or no bubbles, and there's reasons for it, but sometimes it feels random.
Okay, cool.
All right, cool. Anything else?
Yeah, I was just, I wonder if we could go over 8U, because I'm pretty stumped on how that whole mux system kind of works out.
Sure. All right, we have a multiplexer. The basic goal of a multiplexer is to select one of its inputs and send it to the output. Right, so it's kind of like a programmable wire. We can choose to connect D0, 1, 2, or 3 to F. And which one is connected is controlled by setting these inputs S1 and S0. Okay, so here's the table for the mux itself. If S1 and S0 are both 0, then F is coming from D0. Okay, so it's like there's a wire right there. If you switch S0 to be a 1, then F will come from D1, so it's like a wire right there. And D2 and D3 for the other combinations of S1, S0. Okay, now if we look at how this circuit is wired, where the D's are coming from, D0 is coming from whatever A0 is. We don't know its value, but whatever A0 is, if it's a 1, D0 is a 1. If that's low, D0 will be low. So I'm adding that information to this table, right? If S1 and S0 are both 0, F will be equal to whatever A0 is.
Yep.
All right, for 0, 1, F will be D1. D1 is always coming from A1. So F will be equal to A1 in that case. D2 is what? What's the value going into D2?
When D0, because it's going to ground.
It's going to ground, so it's exactly a 0. It doesn't matter what the other inputs are. It's always a 0 going right here. So we can just write that as a 0. And since F is equal to D2 in this case, F is going to be a 0. And then if these are both 1, we've got a 1 going into D3 because that's connected to 5 volts. And so F's going to be equal to 1 in that case. So now take a step back and look at what you're asked to do here, right? Analyze this circuit to obtain its output function F of A, B, A1, A0. So we're thinking of this as a circuit with 4 inputs and 1 output. And the inputs are A, B, A1, and A0. And the output is F. All right, so let's make a truth table. And I'm not going to do the whole truth table,
Yeah.
but we'll do a few of the values. All right, so to fill in the value F, we really just need to read the answer from our description of what the multiplexer does. So S1 is always A and S0 is always B, right? So we can also adorn this truth table by saying this is the value of A and this is the value of B. And so if we use that, we can fill in our value for F. So if A and B are both 0, F should just be equal to A0. So A0 is a 0, 1, 0, 1. If A and B are 0, 1, which is right here, F should be equal to D1, which is A1. So here A1 is a 0, here A1 is a 1. If A and B are 1, 0, then F should always be equal to 0, and so on. And so you can make a truth table like this, and then you've just got a plain old truth table, and you write it in compact min form. So just add up all the product terms where F is equal to 1.
Okay. Oh, okay. I see. 'Cause I think the one thing I got stuck on was how the A and B interacts with A0, A1.
Oh, okay.
That was just kind of my confusion.
Okay.
Yeah. Thank you.
What if you did the truth table where A0 comes before A1? Is that still valid?
Yeah, you can pretty much do them in any order. Usually when I do truth tables and I have subscripts, I'll do the higher subscripts on the left. That's kind of a standard computer science thing. So A3, A2, A1, A0. But as long as you're labeling what's up here, your truth table is going to be valid. There's just sort of conventions. So the usual convention S1, S0, S1 would come on the left. But I suspect not everybody follows that convention 100% of the time. So this is a really interesting exercise, because suppose that you're trying to implement a circuit. Let's say we want to make a circuit of 2 inputs. So we'll call our inputs A, B, and here's our output value F. And I don't know, let's just pick some random function that we want to implement. All right, so we can, take this, we can make a K-map, cover a rectangle, simplify, write a sum of products, get some AND gates, OR gates, inverters, draw a picture, pick pin numbers, all this kind of stuff. We know how to make a circuit that will implement this. But here's a totally different way to build a circuit to implement this function. Get yourself a multiplexer. Four inputs. One output. Let's feed A into here and B into here. And let's take these 3 lines, connect it to 5 volts. Let's take this line and tie it to ground. Bang, I just implemented this circuit. So what does this do? If A and B are both 0, this will take input 0, which is 5 volts, logic 1, send that to F. F will be 1. If A and B are 0, 1, this multiplexer will take input 1, which is a logic 0, send it to F. F will be 0. And in the other 2 cases, S1 and S0, or 1, 0 or 1, 1, it'll take either input 2 or input 3, which are both logic 1, 5 volts, send those to F. F will be a 1. So I can forget about, sum of products, K-maps, minimizations, all that stuff. If I have a multiplexer, I can build any truth table that I want in hardware just by setting the inputs to the 1s and 0s I want in my truth table. And if I had a function of 4 variables, if I have a 16 to 1 multiplexer, I can do the same thing. And I literally just take the values I want my function to have, and I wire my 16 inputs to those values, and I've got my piece of logic. Now there's AND gates and OR gates and inverters and all kinds of stuff inside this block, right? But I'm not thinking about those when I design this. I'm really just sort of taking my outputs and wiring up here, and there's my piece of circuitry. And this is how a lot of programmable devices work. Field programmable gate arrays, FPGAs. When you design a circuit on these, you can specify what you want the truth table to do, and it will basically hardwire the inputs of a multiplexer to correspond to your truth table. So it doesn't usually take AND gates and OR gates and inverters and wire them together. It really just has a whole bunch of multiplexers, and it just sets the inputs based on your truth table. And that's one way programmable logic implements, you know, effectively arbitrary truth tables, arbitrary functions. So this is a really powerful idea if you have a lot of multiplexers, right? So in an FPGA, there's a bunch of multiplexers. They're really, really small, and they get hooked up like this. So that can be a useful trick sometimes. All right, other homework questions?
Truthfully, I haven't gotten to 10 or 11 yet, so I don't know if I have questions on them or not.
Okay. Well, there's still lab hours tomorrow, and there's still office hours tomorrow morning. But let's take another look at some of this programmable logic. So let's take a look at a real world PAL. So if you do any kind of design or manufacturing of electronic parts, you eventually come across DigiKey. And DigiKey is a cool site. It's basically where you can go to buy stuff, electronic stuff. And it's got, you know, I don't know how many hundreds of thousands of different kinds of things on it. But it's got a pretty good search feature, so I'm going to search for PALs. So I'm just going to do PAL. And it'll bring up categories, and the second category is programmable logic devices. So it's got 494 items in that category. So let's bring up some of those. And you can filter your searches, right, by manufacturer, by whether the device is active or not, by how it's programmed, the voltage requirements, how it's mounted, does it work on a proto board or not, and so on and so forth. But I'm just going to go out and semi-randomly pick this thing, which is PAL 16R4, right? So it's a little, I think it's a 20-pin chip. They're $8 a piece. That's kind of expensive, but you know. And there's a data sheet. So I can click on the data sheet, and there's a fuse map. So if we, well, let's go to the top of this. So there's a programmable AND plane, and then there's a bunch of OR gates fed from the output of the AND plane, and there's different versions of this device. So this device is pretty close to the devices we've been talking about. This one incorporates these little boxes that are called flip-flops. These are memory elements. We're going to talk about flip-flops next week, maybe this week. So there's different kinds of devices, and you know, different packages, and so on and so forth. But then there's a fuse map, and you can use this to specify the program for the device. So there's inputs. For example, here's input 1 that's coming in on pin 2, and it's using this notation that I said you're not allowed to use in schematics, but you can use for fuse maps. So it looks like an inverter, but this line coming out of the top is uninverted, and the one coming out of the bubble is inverted. So this leftmost vertical line, that's input I1. And the next line is I1 bar. And this third line, if you trace it down, you're going to find that that comes from over here, so that's input 0. And the fourth line comes from this bubble, so that's input 0 bar. And the fifth line here, that's I2, and the next line is I2 bar, and so on and so forth. So these are, you know, those vertical bars that we were drawing in our fuse map, and these horizontal lines, right, feed the AND gates. And this is actually, you know, a 32 input AND gate, but we just draw it as a single line, and we can put dots here to show which of these inputs should be connected to each of these AND gates. And so these AND gates all feed into this big wide OR gate, and that basically generates your output. So it lets you make a sum of products. And there's extra stuff that we haven't gone over. For example, there's another AND gate here which can be used to go into this thing which is called a tri-state buffer. And a tri-state buffer, it's kind of like an inverter but with an on-off switch. So we can put a signal into the side of this inverter, and if we put in 1, it just acts like a plain old inverter. But if we put a 0 in here, it basically turns it off. It electrically disconnects this from the output. Right? And it's different from just setting the output to 0. It basically removes it from the circuitry. Because if it's outputting a 0, then this is at, ground, and we can't put this pin to 5 volts. But if you disable this device, if it gets removed, then this is floating, and we can drive the voltage on this pin from some other source. So all of these outputs are tri-state enabled, right? So we can turn them on or off. And we can also take the output from any of these and feed it back in to be the input of more AND gates. So we can have feedback paths. But it's the same basic setup of this AND plane we've been working with. But, for a particular device, you get different fuse maps. Here's the one with the memory elements on the outputs, and so on and so forth. And for different kinds of devices, you'll find different data sheets. So here's a different device. This one's obsolete. It says not recommended for new designs. But same idea. There's a fuse map, and that's a little simpler one, right? So inputs feed the vertical lines, and they go into AND gates, and they get ORed and go to the output. So for homework questions 10 and 11, you get to draw your own fuse map, right? And it'll look like, the fuse maps that are in the book. But just to kind of give you an idea of like what a real world device would look like.
Are these electrically programmable ones?
That's a good question. I'm going to guess yes, but let's see. Fully functional, plastic, dependability. Actually, I don't think they are because I don't see a programming option. Their easy programmability allows for quick design of custom functions, typically results in more compact design. Okay. I wonder how you program it. I'm going to guess that these are one-time programmable. Can be programmed using widely available software and inexpensive device programmers. Complete programming specification can be found elsewhere. So yeah, they are electrically programmable, but I'm guessing they're one time. But somewhere in this 24-page data sheet, it probably tells you definitively.
What do you mean when you say one-time programmable?
So if these are actually fuses, you can basically melt a fuse to break a connection, but you can't re-establish that connection. You can't unmelt the fuse.
Oh, I see what you're saying.
Right, so you basically program it once, and then if you want to program it differently, you throw it away and you get a new device.
Oh, okay.
Reprogrammable ones would use something like flash memory, where you can actually change, from a 1 to a 0 and back to a 1. But yeah, that's a good question. I've never played with one of these. All right, cool. This is like Let's Fly Loud Airplanes over Nick's apartment day. So I might have to close the windows. All right, so let's look at some other examples of more complex devices. So multiplexers are one example of something more complex than a simple AND or a NOR gate or things like that. They're built up out of, effectively these simple building blocks, NORs and ANDs and inverters and so on and so forth. But we think of them as, some higher function. We think of a chip that has 2 select inputs and 4 inputs and 1 output, and does, this kind of function, for example. So let's look at some other examples of this. So one example is, let's look at a 74130H. So this is a demultiplexer. So a multiplexer takes in, say, 4 inputs and selects one of them. A demultiplexer chooses one of multiple outputs to drive. So it's nominally something like this. Right, so it's the other direction of what a multiplexer does. It'll pick an input, and it'll pick an output and feed the input to that output. So let's look at one of these in detail. 74138. You'll get to use these in some later labs eventually. So on data sheets, there's usually multiple things being documented in any given data sheet. So this is the 54138. 54 LS138, 74 LS138, and then the same thing for the 139s. So we've got 6 different devices being described in this data sheet, right? It's like when you buy a stereo and you get the instructions, and it's, instructions for 100 different stereos. So the picture we're going to work with is this one here on the left, right? So let's just suppose it's a 74 LS138 or a DM74 LS138M, right? So it looks like this. Fundamentally different from this, which is the 139. All right. So 3 select inputs. So this is a 3 to 8 demultiplexer. So we have 3 select lines, A, B, and C, and we have 8 output lines, Y0 through Y7. And they have the little bubbles on there, so they're inverted. And we've got power and ground, and we also have these lines labeled enable. And this is pretty typical with these more complex chips. Usually you have a collection of these things wired together, and they might be sharing signals, they might be taking turns driving outputs. And so it's typical with these chips that you have the ability to turn them on or off, basically, to enable them or disable them. And so this particular chip has 3 inputs that can be used to enable this device. So if I were to draw a picture of this, I would say it's got 3 select lines. So it would look something like this. And then 8 outputs with bubbles on them. Y0 through Y7, and then some kind of enable circuitry. 3 lines coming in that collectively enable the device. So what specifically do all of these lines do? Well, you've got to find a function table or a truth table, right? This basically tells you when you're going to hook it up, right, which pins do I connect to what. If I have my 3 select lines, I'm going to put those into pins 1, 2, and 3. And it tells you where to apply power and ground, so 16 and 8. So let's find a function table. So 74LS138. And here's what it does. First of all, let's look at the enable. Okay? If G1 is anything, X is a don't care. If G2 is high and G1 is anything, what happens? These become don't cares. A, B, and C have no effect, and all of your outputs are high. So this is effectively disabled. And this G2 has a little asterisk on it. So what's the asterisk say? G2 is the OR of G2A with G2B. All right. So this is where you want to be, like, you know, somewhat fluent with logic operations and things like that, because even in this truth table, they don't actually tell you G2A and G2B. They show you the OR of those. Okay, so if the OR is high, what does that mean? It means either this is high, or that's high, or both. So this first row of the truth table says if G2A is 1, or G2B is 1, the device is basically disabled and all of your outputs are high. Alright, similarly, if G1 is low, doesn't matter what G2 is, doesn't matter what ABC are, all of your outputs are high. So to disable the device, either make G1 low or make one of your G2s high. And that information is actually contained in this original picture of the chip, if you know the secret code. So the secret code is, this is called enable, and G1 is going into the enable without a bubble. It's going into the chip without a bubble. So this means that G1 is what we call active high. Normally we think of, you know, 1 is on or true or active, and 0 is false or off or inactive. So if we just had an input called enable with a line going into our chip, we would infer that that has to be a 1 for the chip to be enabled. If we had a line labeled, you know, sing a song, we would infer that if that input was a 1, then the chip would sing a song, right? So G1 should be a 1 for the chip to be enabled. These two inputs go through bubbles. They're active low. We can think of this as just inverting it. So if we make this a 0, it'll get inverted to a 1. That enable input will be active. It'll be a 1. And same thing here. So from this picture, we can infer that to enable a device, we need this to be low, low, and high. Right? So G1 is high, G2, A, and B are low. And that's spelled out in the truth table. But it's actually coded in that circuit diagram. So G2 has to be low, and both of the G1s have to be, G1 has to be high, and both of the G2s have to be low for this device to do anything. Alright, so all of these columns where the interesting things are happening, G1 is high, G2 star, which is the OR, is low. If the OR is low, it means both of these must be low. Okay, so that's the enable, and most of these devices, they have some sort of enable-disable circuitry. Alright, so assuming that the device is enabled, assuming we're in these lower 8 rows, what does this device do? Well, based on the value of these select inputs, exactly one output goes low. And all the other outputs are going to stay high. And which output goes low, it depends on your combination of ABC. So if we think of ABC as a binary number, 0, 0, 0, hey, Y0 is the one that goes low. 0, 0, 1, that's the number 1. Hey, Y1 is the output that goes low. 1, 1, 0, that's the binary number 6. Guess what? Y6 is the output that goes low. So this is super logical once you kind of know the code. But it takes some practice reading these things and thinking about these devices to sort of get that connection. So what's the punchline on this device? Normally these outputs are high, But if you enable the device and you set ABC appropriately, you can drive one of these outputs to a 0. And these bubbles over here are telling you that these are active low. They're normally 1, but you can select one to go to a 0. If that's a little confusing, you're paying attention. So that's okay. And you can start getting tangled up with like double negatives, like is this Y0 or is it Y0 bar, because there's a bubble and so on and so forth. The truth table will not steer you wrong. Okay, if you really want to know what this device is doing, always come down to the truth table or the function table. But eventually you can look at, you know, the pictures like this and the bubbles and so on and so forth, and you can get that same information. But when you're trying to figure this out the first few times, always go to the truth table, right? And it's completely unambiguous. If G1 is high, if both of my G2s are low, if CBA are low, high, high, then all of my outputs will be high, except for Y3, which will be low. All right, that's an example of a demultiplexer, also called a decoder. And they look like this, right? This is what's going on inside. So you could build this with a bunch of gates, but you know, somebody has done this for us, and we get to just use this. But this can also help if you have, you know, some question that's not answered in the truth table. You can always come down here and figure out what's going on, but it's usually kind of complicated. For example, you know, we have G1 going through an inverter and then going into this AND gate with 3 inverters on the input. And here we have an inverter going into something that looks like a backwards inverter. Well, this is just a plain old inverter, but it's drawn differently. Why? Well, there's reasons. but you know, this will also tell us the absolute truth of what's going on with this circuit. And then the rest of this particular data sheet is the physical data. So if you get this in the form that works in a proto board, right, there's a 95-degree angle between the pins and the horizontal at the base of the chip. Do you care about that? Maybe, maybe not. Usually we just bend the pins until it fits in the proto board. But if we had a machine building a circuit board for us, and it was going to pick up the chip and place it through a bunch of holes in a circuit board, the machine might have to bend those pins. Well, how much should it bend them? Well, you know, 5 degrees typically, if it's going straight down. So we've got mechanical information, we've got dimensional information, and then usually ordering information. And don't use it for life support or other critical missions. All right, so that's one example of a more complex device. Let's take a look at another one. This one is even stranger. So this is called a priority encoder. '74LS147. We're not going to look at the 148. So the 147, 16-pin device, basically encodes 8 data lines to 3-line binary octal. What does that mean? Who knows? Let's look at the truth table. All right, so over here on the left, 147. So we have 9. Let's do 148. Stick with binary. So we have 8 inputs and we have 3 outputs, and we have some other stuff. I'm going to ignore these. 3 outputs, 8 inputs, and an enable input. Now, if the enable input is low, then the outputs are just all high. Sorry, if the enable input is high, the outputs are all high. So that's the uninteresting position. So EI has to be low for this device to do anything interesting. So what is this device doing according to the truth table? Any guesses or interpretations?
It's just trying to convert your inputs as a binary number to an octal number for the outputs.
That's the effect of it, yes. But it's doing it in a very peculiar way. For example, if all of your inputs are high, all of your outputs are high. If input 7 is low, it doesn't matter what the other inputs are. All of your outputs are going to go low. If input 7 is high but 6 is low, it doesn't matter what the other inputs are doing. Your output is low, low, high. So this is kind of a strange mapping from input to output. So the first thing is these outputs are what we call active low. And one hint to that is that when we disable the device, all of the outputs are high. So we're going to think of this in a kind of backwards way. I'm going to think of this as a way to count in binary, but I'm going to use the opposite value of A0, 1, and 2. If these are all 0, I'm going to consider that to be the number 7. If my inputs are 0, 0, 1, I'm going to consider that to be the number 6. If my inputs are all 1, I'm going to consider that to be the number 0. Why? I don't know, but I'm allowed to do this, right? This mapping from patterns of 1s and 0s to integers is effectively random or arbitrary. Now, if we're doing arithmetic, we want weighted positional notation, all that kind of stuff, but this is a perfectly legitimate mapping from patterns of 1s and 0s to numbers. And it's the exact opposite of what we normally do when we do weighted positional notation. So this is sometimes called negative logic. And the idea is we're thinking of a 1 as being off and a 0 as being on. So this is off, off, on, that's the number 1. This is on, that's the number 7. Alright, so just take that as, if somebody was having a weird day, they decided this is going to be a 0, this is going to be a 7. But if we take that as given, and we look at our outputs here, what is this? This is low, 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 0, 0, 0. That's a 7. This is a 6. This is a 5, 4, 3, 2, 1, 0. Now, if we think of these numbers as representing those integers, right, going from 7 down to 6 down to 5, take a look at the inputs. This 7 corresponds to the fact that input 7 was low. This 6 corresponds to the fact that input 6 was low, but 7 wasn't. This 5 corresponds to the fact that input 5 was low, but 6 and 7 were not. So what this circuit is doing is, if we think of these inputs as having priority levels, where 7 is the highest, it's telling us what's the highest priority input that's set to low. For example, in this row right here, the highest priority input that is set to low is input 4. right? This is high, this is high, this is high, but input 4 is low. That's the highest priority. And the output is low, high, high, 0, 1, 1. That's the number 4. So this is the device for detecting priority. And the idea is we have inputs, 8 possible inputs, and we're interested in knowing when an input is low, more negative logic, right? If the input is high, we consider it to be not active. But if the input is low, something interesting is happening on that input. And this device lets us know which is the highest priority input that has a low on it. And if we look at this and we see this number high, low, low, we translate that to a 3. That tells us input 3 is the highest priority that has a low on it. Now these could be low, they could be high. We don't care, they're lower priority. 3 is a higher priority than those. These have higher priority, but they're all high. They're not active. So that's what this chip does. And again, you know, you can build it out of AND gates and OR gates. You get this circuit over here. But there's a chip we can buy for a few pennies that does this for us. So the unanswered question is, why do we care about this? Why do we want a chip that does this for us? So we can put multiple inputs in. This will tell us the highest priority input that's active. Well, we use something like this, say, in a computer. And I should have asked this week 1. How many people here are computer science focused as opposed to electrical engineering? Do you do a hands up or a chat or something?
I'm a little bit
Computer
of both.
science focused.
A little bit of both.
In like programming.
Okay.
Software, yeah.
Okay. Usually there's a lot more computer science than there are electrical engineering. So inside a computer, you have a CPU, and if you only have a single CPU, it's got to do all the processing. Whether it's you know, adding 2 and 2, or compiling a program, or responding to a keystroke, or picking up a piece of information coming in through the network, the CPU's got to deal with it. Right? And there's lots of stuff going on in your computer all the time. You're sitting there not doing anything, but there's hundreds of processes running in the background on a typical machine. And how does it decide what needs attention? Right? So it could continually say, hey, have you pressed a button yet? Hey, have you clicked the mouse yet? Hey, is anybody talking to me on the network? Hey, how's the power level? Are we having a power failure? Hey, is the temperature getting too high in the CPU? Right? If it had to do that, it would spend its whole life just asking these questions of these different systems. So we use something called an interrupt. And when we get to 270, you'll learn all about interrupts. But an interrupt is basically, hey, whatever the CPU is doing, stop what you're doing. I got to talk to you for a minute. Okay, it's like when your phone rings. So when you interrupt the CPU has to figure out, hey, who's trying to talk to me right now? Well, it could be that, you know, the mouse button just got clicked. It could be that a packet just arrived through the network interface. It could be that an alarm just went off in the temperature monitoring system and our CPU is about to melt. Right? Which one of those should the CPU deal with first? Probably the temperature alarm. Right? Probably the only thing more critical than that would be a power failure. Somebody hits a key on the keyboard, you can wait 1 billion cycles and the person's not going to notice, right? Because humans are slow. But these other things are going to be higher priority. Now, network traffic coming in, that's higher priority than the person typing a key on the keyboard, right? But it's lower priority than the CPU is running at 120 Celsius and is about to melt. So you need to prioritize how you look at requests for information. You could use this chip exactly for that. You would have an interrupt line coming from different sources, and you prioritize them. You put the highest priority interrupt on that line 7. And over here on lines, 1 or 2 would be your interrupt from the keyboard being pressed. So let's say someone presses a key on the keyboard, so this input is low, and a packet arrives from the network, so this input is low, and the CPU is melting, so this input is low. Well, the output of this chip is LLL, that translates to a 7. Hey, event 7 is occurring, that's the CPU melting, I gotta go turn the fans up or something. Right? Instead of going through and checking each line and deciding in software, which one is the highest priority. So that's an example of where this kind of chip could be used. And this is actually called a priority encoder. And you can cascade these together. If you had 16 events you wanted to prioritize, you could do that with a pair of these and some other logic. All right, so this is a good place for a 5-minute break. And then I want to come back and I want to start looking at a different dimension to all of this. I want to bring the time dimension into the behavior of circuits. This will be a preamble to where we go probably next week when we start kind of the second half of the course. But I want to get some initial inroads into that topic, and then Thursday we'll probably talk about some more complex circuitry, including adders, which will be a setup for the next lab you're going to do. So let's take about a 5-minute break and come back, and we'll start looking at the role of time in all of this this digital business. All right, so let's look at a new dimension to all of this. So let's bring up a data sheet for a good old inverter. So 74LS04, straight inverter, and we know that if you put a 0 in the input, you get a 1 on the output. If you put a 1 on the input, you get a 0 on the output. About the simplest behavior you could imagine except for a wire. So there's the function table. But in practice, these things are physical devices. There's transistors and resistors and diodes and wire, and even going through a piece of wire takes time, right? If you put a voltage on one end of a wire and that wire is a foot long, it takes a nanosecond for that voltage to reach the other end. It actually takes longer than that, but speed of light would be 1 nanosecond per foot. So there's a time delay. And in practice, if I have an input of 0 and my output is 1, and then I raise my input to 5 volts, it takes a little while for my output to drop. Which means that on paper, we always think of the output as being the opposite of the input, but guess what? When I first raise the input to a logic 1, there's a brief period of time when my input is 1 and my output is also 1. And that can be a problem. Sometimes doesn't make any difference. If this is connected to an LED and we're looking at it, and we flip a switch so our input is 1, our output goes to a 0, the LED goes off, we don't notice that it took a nanosecond for that to happen. Right? So that's not a big deal. But in some cases, this can be an issue. So how long does it take the output to respond? Well, it depends on the type of device that you're working with. And it depends on whether it's, 7404 or 74LS04 or an HC04 or what particular type of inverter you have. But on your data sheet, you'll find a thing called switching characteristics. And we looked at these briefly already once, but we're going to look at them again. So from the input A to the output Y, it takes some number of nanoseconds. We're seeing numbers like 8, 15, 12, 22 nanoseconds. That's a pretty long period of time in a computer. All right. So these are called propagation delays, and the timing is T sub PHL, so propagation delay from low to high. This is the time it takes your output to change from a 0 to a 1, and it's typically 12 nanoseconds, but guaranteed no worse than 22. The propagation delay for the output to go from high to low, that's the case we had where the input went high, the output should go low, typically 8, no more than 15 nanoseconds. All right, so let's get a handle on frequencies and such. So 1 nanosecond, that's a period of time. Okay, it's a billionth of a second. But if you had something which changed, which cycled with that period, in other words, something that's going high and low and high and low, and the time from going high to the next time it goes high is a nanosecond, what's the frequency of that signal? How many times is it changing per second? So if this is a billionth of a second, this will be a billion. So 1 billion cycles per second. So a billion we write as giga, and cycle per second we write as hertz. So that's what a gigahertz is. It means that something's changing repeating itself every nanosecond. All right. So 1 nanosecond corresponds to a gigahertz. 10 nanoseconds, so it takes 10 nanoseconds to cycle. It's going to cycle 1/10 as many times. That's a tenth of a gigahertz. So 0.1 gigahertz, which is the same as 100 megahertz. 20 nanoseconds will be half the frequency, that's 50 megahertz. Okay, what's the clock speed of your computer? Is it more than 50 megahertz?
On the CPU?
Yeah.
4 to 5 gigahertz.
Yeah. So we're in the gigahertz range, right? I have like a 2 gigahertz CPU because I bought it from Best Buy. But, you know, 3 gigahertz, or if you're overclocking, you know, maybe 3.5, 4, multiple gigahertz, right? Suppose you had a CPU running at 5 gigahertz. That's a fifth of a nanosecond, 0.2 nanoseconds. Or if you go down to the next multiple of 1,000, 200 picoseconds. So computers, really, really fast, really short periods of time. This device, really, really slow, 20 nanoseconds. That's equivalent of 50 megahertz. Okay, my first computer was 66 megahertz. That was a long time ago. So for a computer, this is an eternity. Which means that, you know, when our input changes, our output might be at the wrong value for a huge amount of time in the mind of this computer. So flipping a switch, turning on a light bulb, we don't have to worry about this. Changing an input and using that to control the state of a computer, we definitely have to worry about this. And the second half of the course, we're basically designing the kinds of circuits that are built into computers, what are called state machines. And a computer is really just a really complex state machine. So as we move forward, these are going to become critical issues for us. So let's see where something like this could give us an unexpected result. So let's build a circuit, or let's design a circuit. And I'm just going to use an AND gate. And I'm going to put an inverter here. And I'm going to use my trick of labeling intermediate points so that I can draw a truth table for this. So A is really the input to my circuit, and that's going to be a 0 or a 1. And I want to know the output X. But let's fill in this intermediate point B. So B is the output of an inverter that's connected to A. So it's going to be the opposite of A. And X is an AND gate. And what are the two inputs, A and B? Well, 0 ANDed with 1 is a 0. 1 ANDed with 0 is also a 0. So from this analysis, it looks like my output X is always going to be a 0. And logically, you know, I've said X is A ANDed with A bar. And there's actually an identity, if you look up the part of the book that talks about Boolean identities, which says anything ANDed with a negation of itself is going to be 0.
But it wouldn't always be 0 because of the propagation time, right?
But because of the propagation time, it's not always going to be 0. So a truth table shows us kind of a static picture, and it's based on idealized behavior of these chips. If my input here is a 0, this is a 1, end of story. If this is a 1, that's a 0, end of story. But to actually see what happens in a real-world situation, we need to introduce time. All right, so we're going to use something more powerful than a truth table. We're going to make what's called a timing diagram. And a timing diagram is like a truth table, but we're going to have time drawn horizontally, and we're going to have logic levels sitting on this vertical axis. So let's analyze this circuit with a timing diagram. And we'll be doing lots of timing diagrams later, but again, this is kind of a first introduction to it. So time runs this way. And I don't know what exactly I'm looking for, but the question is, you know, as A changes, as it rises and drops and rises and drops, what exactly happens to X? So I'm going to label an input here A, and I'm just going to draw a waveform that shows it low and then high and then low and then high. Right, because I believe something interesting will happen when A changes from 0 to 1, or maybe from 1 to 0. Alright, so now I'm going to draw a picture for B, and we're going to take into account this propagation delay. So normally if A is low, we expect B to be high. And at this point in time, A is rising. A goes from 0 to 1. And we expect B to respond by going from a 1 to a 0. But we know there's a propagation delay. Okay, I'm going to exaggerate that delay. I'm going to come way over here until B drops. And this period of time, that's my propagation delay from my output going high to low. Doesn't matter what we call it. But this would be, you know, 10 nanoseconds, 20 nanoseconds, depending on the device, the data sheet. But there's some delay. It's not instantaneous. And, you know, after things have settled, A is high, B is going to stay low. And now, at this point, A is going to drop. And again, there's going to be a propagation delay. There's going to be some period during which B stays low until its circuitry eventually responds, and it goes high again. So there's some other propagation delay. Delay from low to high. Okay, now let's look at what X does. So X is ANDing its two inputs, A and B. Well, we've got a 0 and a 1. That's going to be a 0. All right. At this point, the two inputs A and B are high. If you two inputs to an AND gate are high, the output of the AND gate is 1. Right? So ignoring the fact that the AND gate also has a propagation delay, it looks like at this point the output of the AND gate is high. And now at this point B has gone low, so the output of the AND gate is low. And at this point A has dropped, B is still low, so we still have a 0 and a 0. And now B goes high, but A is low, so that's going to stay low. So mostly our output is low, except right here, the two inputs were temporarily both 1. And it's a little more complex than that because there's some propagation delay associated with the AND gate. So at this point, both inputs are 1, but the AND gate's not going to respond immediately. It's actually going to take a little while. And an AND gate probably has a longer propagation delay. So it may be somewhere over here we see a 1 coming out. And then eventually we see a 0. But regardless of where this little bump is, this bump is present. And that's called a glitch. I just rewatched Wreck-It Ralph the other day. So, glitch, same thing. That's a glitch. That should not be there. Right? If you look at the truth table, X should always be a 0. But hey, guess what? In practice, there's a little brief moment in time when x is a 1. Everybody see where that comes from? Even if the placement of it isn't clear.
Yeah. If will we have to draw these more accurately? Like, what is the propagation delay rated for this chip, and then that would be the propagation, or is this just like an abstract? This is probably going to propagate first. This might propagate second, and this might propagate third. So visualize what the delay will be.
So yeah, good question. So in a typical, homework or test question, I would say, assume the inverter has a propagation delay of 10 nanoseconds and the AND gate has a delay of 20 nanoseconds. Show me, and suppose A does this, show me what the B and X signals look like. And I'd give you a piece of graph paper and say each of these is 5 nanoseconds, right? And you'd fill it in. But the most important point is sort of the more abstract notion that when this changes, it takes some time for this to change, and so there's a period when these have a value that we didn't expect from the truth table, and that can cause other points of our circuit to have values that we didn't expect. And this can be a problem, right? It's a pretty short glitch, right? If this was 10 nanoseconds, right, this glitch is only going to be 10 nanoseconds wide, right? But 10 nanoseconds, if your system is running at 5 gigahertz, right, in 10 nanoseconds, it's going to do 50 things. Your CPU's clock is going to toggle 50 times. That's going to be 50 clock cycles during which you expected the output to be a 0, but it was actually a 1. And if that is feeding into a piece of circuitry that says, hey, if this input is a 1, shut down the entire system because something catastrophic is happening, that might be enough of a glitch, that might be long enough of an event to cause your system to shut down. Or to cause your city's power grid to shut down. Or who knows what. So glitches are a big source of concern. And the faster computers get, the more critical these glitches become. And so... No, go ahead.
But really, the faster the computer goes or chips go, the less room for error there is.
Yeah. Because, in the case of a human operator, where it says, if this light turns on, shut down the main power. Well, if this light blinks for 10 nanoseconds, you're not going to notice it, right? Mm-hmm. So that's one extreme. On the other extreme, if you have a machine that's monitoring this and it checks it 50 times, well, this is high, right? It's definitely going to notice, oh, that's high, I better shut down the system. So for quite some time, most of the circuitry that we've designed in digital electronics incorporates what we call a clock. And the idea of a clock, which we're going to talk about more next week, the idea of a clock is we only look at your signals at certain points in time. And we arrange things so that all of these glitches occur in between the times that we're looking. And when you have a CPU with a clock like a 3 gigahertz clock, that's saying 3 billion times a second the circuitry is looking at what's going on. But in between those ticks of the clock, it's basically ignoring what's happening. That's the time when all of these glitches happen. That's the time when everything moves from one state to another. It's the nighttime rearrangement of everything. And then in the morning, you look at the world and you see what's going on and you make your decisions. And then the sun goes down and all the things change and everything gets weird and strange, but you don't notice it because you're only going to look when the clock ticks again. So that's basically how we move from digital circuits like we do in 120 or like we've done so far to computer circuits. And almost all computers are clocked. And this uses what we call synchronous logic. Synchronized meaning there's a clock. Now you can do asynchronous logic. It's a lot more complex, but it's faster and it's richer. But mostly we use synchronous. All of our laptops and phones and other devices have some sort of clock inside. And the clock governs when things happen. All right, but this is part of the reason for clocks, because these glitches can occur. So there's sections in the book that talk about glitches, and also talks about using K-maps to identify glitches and how to deal with glitches and so on. And I'm skipping over those parts, right? If we have time at the end, we'll come back to them, but for now we're skipping over those. But I want you to understand the concept of where these come from, and we're going to get a lot of practice making timing diagrams. That's definitely going to be a tool we want to be pretty comfortable with by the end of the course. All right, other questions about that? All right, so we'll have more to say about that when we start working with what's called sequential circuits or sequential logic, where we have things changing over time. But let's go back to looking at the kinds of circuits we've been building so far, where we don't worry about glitches, where we just have inputs and we have outputs. And let's look at our next complex device, which is an adder. And this is going to be the subject of your next lab, which you still have some time before we start it. But, you know, digital logic, computer chips, what do we want to do with computers? Well, it's nice to be able to do math, right? And what's the most basic type of math we can do? We can do addition. We can do logic operations, but we don't usually think of that. Usually we start by thinking of addition. So, you know, how do we add numbers? Well, I don't know. It was a long time ago I learned. But we know how to add numbers, right? And we've started doing some addition in binary right in the beginning of the course, where we said, you know, we could write the number 2 like this and the number 3 like this, and we can add this the same way we add bigger numbers in decimal. 0 plus 1 is 1, 1 plus 1 is 0 with a carry, 1 plus 0 plus 0 is 1, 0 plus 0 is 0. And what's this? Hey, that's the number 5. Magic. All right. So we can add, you know, binary numbers like this, but the steps of that are fairly complex. For example, we had to know 0 plus 1 was 1. We had to know 1 plus 1 is 0 with a carry. And we had to know 1 plus 0 plus 0 was a 1. Now, you and I can do that. We can just memorize it. But how would we build a piece of circuitry to do that? So let's look at the design of an adder. And we can do the same thing we've been doing all quarter. We can write a truth table. We can turn that into equations. We can minimize it. We can make a circuit. So let's see how this works. Let's make a 1-bit adder. So we're going to put in 2 bits, A and B, and we're going to generate a sum. But we also need to generate this carry bit, right? In other words, if we have 2 numbers, A and B, and we just think of the sum, right? The sum when A and B are both 1 is 2. Well, 2 is not a binary number. So our sum actually has 2 bits to it. So I'm going to write sum 1 and sum 0. And we're just going to write the sum as a 2-bit binary number. Everyone with me so far?
Wait, so how'd you get the column with sum again? Like, why are there two ones?
Two ones. Oh, like here? So 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2.
Oh, okay, sorry, my bad.
That's okay, so we're just adding two 1-bit numbers. And so I'm going to write my sum, and I'm going to use sigma to be all fancy like. I'm going to write my sum as a 2-bit number. 0 plus 0 is just 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2. Well, we could build a circuit to do this. It's not that hard. We can make, you know, K-maps for these and write equations for them. And we can come up with an algebraic expression. Can anybody see what the expression for sigma 1 would be in terms of A and B?
Would it be A and B?
Yeah, that's just a straight AND gate. Just A and B ANDed together, that gives us sigma 1. And sigma 0, we could do a sum of products. So it looks like A bar B or A B bar. So that's not bad, right? That's relatively simple logic. And this actually turns out to be the complement of an XOR. So if we have like a 7486, an XOR gate in our parts box, and an inverter, we can generate this pretty easily. This is just an AND gate. So a 1-bit adder, really not bad. But if we...
You want to go up in bits.
Yeah, what happens if we want to go up in bits? So if we try to do 2 bits, that's going to be a little more complex. So let's picture an adder. And I'm going to put in a 2-bit number A, A1, A0, and a 2-bit number B, B1, B0. And I'm going to generate a sum. Okay, so system diagram. Remember, we've said you have to specify what the inputs and outputs mean. Really important here. Because, you know, what do these 4 inputs mean? So I'm going to write something like this. A1, A0 equals first number. A1 equals the most significant bit. A0 is the least significant bit. Okay, that's important, and that's not necessarily understood. It's sometimes, in some places, A1 would be the least significant bit. Right, so we have to specify that. B1, B0 equals our second number. B1 equals most significant bit. B0 equals least significant bit. So if A1, A0 is equal to 1, 0, that's the number 2. If it's equal to 0, 1, that's the number 1. That's what it means by the ordering. This is the most significant bit. All right, what's the largest sum I can get if I add two 2-bit numbers?
4 or 3.
So what numbers would I add to end up with 3?
1 and or binary 2, which is 0, 1, 0, and then binary 1, which is 0, 1.
Okay, so 2 plus 1 would give me 3. Is there any combination of inputs that would give me a bigger sum?
You could have an 8 if, is this 4-bit or,
So each of these numbers is 2 bits.
The highest value is 6, right?
Highest value is 6 because the biggest my inputs can be are 3 and 3. So my sum could be anywhere from 0 to 6. which, you know, back to a homework question from chapter 1, that means we need 3 bits to represent the sum. Because 2 bits would only get us up to 3. 3 bits will get us up to 8. Well, we can't actually generate an 8, but we still need 3 bits. So I'm going to call these sum bits sigma 0, sigma 1, sigma 2. And I'm going to say sigma equals A plus B. And this is addition. And sigma 2 is the most significant bit. Sigma 0 is the least significant bit. And we've got to make sure we're clear on what these things mean, right? If sigma 2 is the least significant bit and sigma 0 is the most significant, so this is the 1s, 2s, and 4s place, we're going to get a totally different system in the end, right? So we're just defining these and pinning them down. But once we understand these, now we can make a truth table. And our truth table gets pretty big pretty fast. And I am going to write this one out completely. Well, maybe. Apparently I am. Alright, so there's the 16 combinations of A0, A1, B0, B1. And I'm going to write down in here the values of B and A in decimal. So if we just look at A is the numbers 0, 1, 2, and 3. Agreed? 0, 0, 0, 1, 1, 0, 1, 1. And same pattern here, A is 0, 0, 0, 1, 1, 0, 1, 1. Alright, what's the value of B in these first 4 rows? The number B, if I thought of it as a decimal number that I'm representing in 2 bits, what's the decimal value of B in these first 4 rows?
It would be 0.
It would be 0 because both bits are 0, B1 and B0. What about in this next block of 4 rows?
It would all be 1, right?
Exactly, they would all be 1. And how do we know that they're 1 and not 2? We know they're not 3 because 3 is going to be 1, 1. But how do we know that this is the number 1 instead of the number 2? Because we specified in our system diagram the significance of the bits. And we said B1 is the most significant bit. B0 is the least significant. So 0, 1 is the binary number 0, 1, which is the decimal number 1. Whereas here, B1 is a 1, B0 is a 0. That's the binary number 1, 0, which is a 2. But if you don't specify this and write it down, these can flip. And that's going to be a lot of confusion and lost time in the end. Alright, and if B0 and B1 are both 1, then B has got to be a 3. So these 16 rows represent 16 combinations of values of A and B, where each of A and B can be either 0, 1, 2, or 3. And since this is an adder, since sigma is supposed to be the result of adding A and B, let's write this down in decimal. And let's just add these two numbers together. 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6. So that's what we want our circuit to do. But we can't write a truth table with 3s and 5s in it. We got to use 1s and 0s. So let's write down the 3 bits that make up sigma. And I've said sigma 2 is the most significant bit. So I'm going to write this like this. And now I'm going to write the 3-bit number corresponding to this decimal value. So 0, 0, 0, 0, 0, 1. That's the number 2. That's the number 3. And this is really good practice at doing binary to decimal conversion. And you'll get to do this a bunch of times in Lab 4. But now I've got a truth table. I have a truth table with 4 inputs and 3 outputs. Right? Just like my system diagram, 4 inputs, 3 outputs. All right. This is Engineering 250 week 1. This is Engineering 120 week whatever, right? You start with a problem, you make a system diagram, you draw a truth table. Okay? All of that work has been going into producing this truth table. At this point, we can forget about all of this. If we wanted to build a circuit, we've got a truth table, we can start writing equations. So our circuit, you know, it's like our traffic light system. We got some inputs, we've got some outputs. So we're going to have 3 outputs. Sigma 2 is going to be, you know, a 1 right here, 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 and here. There's 6 minterms that are going to get ORed together. Sigma 1 is going to be 1 in those spots, those, and those. That's 8 minterms that'll be ORed together. And sigma 0 will be 8 minterms ORed together. That's a lot of logic, right? Each of those minterms has 4 inputs, either true or inverted, right? So this is going to be B1 bar, B0 bar, A1 bar, A0, all ANDed together. And that's 1 of 8 things that are going to go into an 8-input OR gate. We can do this, but it's really, really expensive. And it's a really complex circuit in the end. But ignoring the practicality of it, right, is everybody comfortable with the idea that if we did this, and we wrote down the equations for this, and we minimized, and we built a circuit, we would end up with something that we could feed 2 2-bit numbers into, and we get a 3-bit sum out. And it would always be the arithmetic sum of those 2 2-bit numbers.
They need some practice.
Yeah, definitely. But like I say, Lab 4, you're going to build this circuit and you're going to analyze it a number of ways. So you'll get a lot of chances to do this and think about it from different perspectives. And then ultimately, when you actually build a 2-bit adder, you're going to throw all this away. And you're not going to do it like this because this is way too complex. We're going to learn a different way to implement an adder. Because imagine trying to make a 4-bit adder. Right, something that just adds 4-bit numbers together. Well, 4 bits for A, 4 bits for B, that's 8 bits of input. That's 256 rows in your truth table. And then you're going to have 5 outputs, so you're going to have, you know, 1,280 some output bits that you're going to have to generate. Imagine making a 64-bit adder. 64 bits for A, 64 bits for A. That's 128 inputs. That's 2 to the 128th rows in your truth table. That's definitely not practical. So we'll learn a different way to design an adder. And it will be a lot simpler than this, but it will be built on the basic idea of being able to add 2 single bits. All right, so that's something that's coming up. All right. Other questions?
No, but I'm gonna have to rewatch this about 3 times in order to completely understand it.
Okay. And one suggestion would be start watching part of it, but once you understand what we're trying to do, try to make this yourself, right? If you understand this and you understand what the output should be in response to the inputs, right? Stop watching at that point and try to make this truth table. That's a lot more fun than watching me do it, right? And it's more instructive, and you can do that with all of this stuff. So that might be more interesting to do than watching. And that's ultimately what we do in the labs, right? The labs are really kind of a hands-on version of doing some of the things that we talk about and do in class. But hands-on is always, a lot more fun to do. So we'll definitely go through this more when we talk about Lab 4. But I wanted to put this out there as an initial introduction, and then, like I say, we're going to find a better way to do addition. That's going to work in general and would let us make, a 64-bit adder without a whole lot of difficulty. And that's the kind of thing that we do when we design large-scale chips. All right, so next time I want to... so I'm going to post some homework. So your homework 3 is due tomorrow. I'm going to post some new homework from Chapter 4. But it's probably not going to be all of Chapter 4. I'll probably break it into 2 weeks. So always when you go to Canvas and you look at the homework, make sure you read what I write in the assignment when I say, work on these problems or ignore that problem or this thing means that and so on. Right? That'll save you from working on stuff that we haven't gone over yet, for example. Because Chapter 4 is going to span a number of weeks. So I'll post some initial problems from there. And we'll talk about those on Thursday, and then I want to talk about some more large-scale devices, something called a 7-segment decoder, 74LS47. We'll talk about that, and I might talk about the 555 timer. And then I'll probably get started on looking at this next class of circuits, these things that change over time, which is, the other half of the course. So probably we'll get started on that towards the end of Thursday's lecture. So keep hitting the homework. Come by office or lab if you have questions on that. Keep working on your lab. Let me know if you got questions with that. Have a good afternoon, and I will see you on Thursday, if not before.
Thank you.
Thank you.
All right, thank you.
Thank you.
Thank you. Have a great day.
You too.
Thank you.
Thank you.